This is the Precalculus 2 notes for section 5.2. The next three sections are going to concentrate on advanced trig formulas, which means you will have lots and lots of fancy little ways to manipulate trig expressions that will all come in the state of formulas. So the first concept that we're going to be talking about for this lesson is going to be the sum and difference formulas. So in order to better show you how these work, let's start with a misconception. So let's just say that you had the cosine of 40 plus 20. Okay, it fits very reasonably in a math student's mind that this could very well be equal to cosine 40 plus cosine 20. Why? Because this distributive property is one of the more famous concepts or properties that students understand and know. So let's just take a look at this and see if this is actually true. So we know that this is 60, right? So if we do the cosine of 60 right now, we're going to get, on the calculator, we're going to get 0.5. If we do the cosine of 40, we're going to get about 0.77. And if we do the cosine of 20, we're going to get 0.94. Okay, so we're looking to see if these two sides are the same. Well, if you inspect this, we clearly see that the right side is going to be way larger here. So this is definitely not going to be the same. So what does that mean? That means the distributive property clearly does not work when it comes to sums and differences of trig functions. So that's the first thing you want to really store in your brain so that if you see something like this, you don't make that mistake. So what are the formulas that actually do work? Well, you see them here. These formulas are sort of bizarre looking, but they're going to get even more bizarre. But for now, these are the formulas that you're going to be applying on exam situations, homework, labs, etc. You'll see the key is let's start with just sine, for example. So if you look all the way across the row, you first have the sine of a sum of two things, and then over here, you have the sine of the difference of two things. You'll see that the pattern in the formula is exactly the same, except whenever there's a plus sign over here, there's also a plus sign over here. When there's a minus sign over here, there's a minus sign over here. That's actually going to change in cosine, so that's definitely something you want to sort of keep in your brain. If you go down to the next line on cosine, when you see the cosine of a sum and the cosine of a difference, you'll see again the patterns and the trig functions on the right side are the same, except now the signs are going to be the opposite of what you see from left to right. So these are the things that you sort of want to keep in your brain as you're going through this. Obviously, it would be nice to get these stored in your brain. It'll make things run faster, but that's not required as of this minute. So how do we apply all these wonderful scenarios? Well, we start with a couple problems that really push home how to actually accomplish this. So the key is going to be to find the exact value of these trig functions. So look at number one. So sine of 105. Yes, we could clearly just type this into the calculator, and if we did, we would get something like 0.97. The thing is that is not an exact value, that's an approximate value. Anything you type into the calculator and create a decimal answer that you need to round is approximate. So in the scenario, we're looking for an exact answer. So how do we do that? Well, we do it using the sum and difference formulas over here. So the key is we want to change the sine of 105 into the sine of the sum or difference of two angles. Well, 105 is not a familiar angle to us, but we do have several other angles that are familiar to us and create exact values based on previous content. What angles are these? Well, they are, for example, just to start, 30, 45, and 60. These angles provide exact trig evaluations with radicals or without radicals. For example, 1/2, √2/2, √3/2, those types of things. Those are exact values. So we could, and by the way, we could also talk about like angles like 90 degrees or 180 degrees, any 270, all those angles create exact values. So we want to look at 105 and see, well, is there any way we could take a pair of these angles with their sum or difference and create the angle 105? Well, hopefully you can quickly see that you could add 45 and 60 to get 105. Now, this just takes a little bit of guesswork, but generally that's what you would have to do. So how is this useful to us? Well, this is actually going to be the sign of a sum, which is actually located at the top over here, this formula right here. And if you look at the sign of a sum, we actually have a formula for how we can actually manage to accomplish that. So let's take a peek at what that looks like. So what is this equal to? Well, according to this, 45 would be u and 60 would be v. So if we were to change this into the formula, then we would say, okay, the sine of u, which is 45, times the cosine of v, which is 60, plus, remember the sine is the same in the sine formulas, cosine of u, which is 45, and the sine of v, which is 60. Okay, so why is this useful? Because all four quantities over here, we can find the exact values for. So just to be clear, you guys are used to doing this in radian language. So let's just, 45 degrees is the equivalent of pi over 4, and 60 degrees is the equivalent of pi over 3. So if we want to find these values, we should be able to do that quickly. And what's really cool is that all of the angles that are in this problem are in quadrant 1, which means all of them must be positive. Is that always going to be the case? Not necessarily, but in this one it will be. So first things first, sine of 45. Well, we know the 45-degree angle, or pi over 4, is √2/2, √2/2. So the sine of in the first quadrant is going to be the y, which is √2/2. Okay, 60 degrees, or pi over 3, is 1/2, comma, √3/2. So if we want to take the cosine, it's going to be the x-coordinate, and that's obviously in quadrant 1, so it needs to be positive. Moving on, cosine of 45, that's going to be the x-coordinate of our pi over 4, which is again √2/2. And the sine of 60 is going to be the y-coordinate of our pi over 3, which is √3/2. Okay, the only thing left to do is to multiply and collect like terms, or simplify essentially. So root 2 times 1 is √2, 2 times 2 is 4. Over here, √2 times √3 is √6, and 2 times 2 is 4. So if we simplify this, these have a common denominator, so we're going to get √2 plus √6 over 4. Believe it or not, that is the answer to the problem. That is your exact value. Now, a couple small things. So remember, you cannot add √2 and √6. So just to be clear, so √2 plus √6 is not equal to √8. Remember, radicals when it comes to adding and subtracting are treated like variables. So we basically have one √2 and one √6, which are not like terms, so we can't put them together, which makes this the answer to the problem. Okay, so number 2, a little bit different. So this time we're looking at the tangent of 15. So if we could make tangent, this 15-degree angle, equal to the sum or difference of two angles that we know, which are these, then we would be set to use one of the formulas above. So notice these are tangent formulas. So usually, if I'm in class, students will pick a couple different pairs. So for instance, we could literally go right back to these angles and go, okay, well, we could do 60 minus 45, and we could get 15, right? But just for argument's sake, just to do something different, we could also do 45 minus 30 in order to get there as well. So I'm just going to use that one. It wouldn't matter in practice if you did, but I'm just going to do that just to do something different. Okay, so again, we have the difference. If we put tangent 15 in the calculator, we're going to get a decimal response, which is not the exact value. We want the exact value is going to be, some type of value that doesn't have decimals in it. It could be a fraction, radicals, usually radicals, some type of an expression. So here we go. So the tangent of 15, we're looking for the tangent of a difference. That is right here. So we basically just need to copy the formula with the values in it. So we know that this is u and this is v. So what is this equal to? The tangent of 45 minus the tangent of 30 all over 1 plus the tangent of 45 times the tangent of 30. Okay, again, if we go back to our knowledge here, remember 45 is again pi over 4, which is root 2 over 2, root 2 over 2. We are in quadrant 1, so we don't have to worry about negatives. 30 degrees is now pi over 6, which is going to be root 3 over 2, 1/2. These are all things hopefully you know by heart so that you're crisp going through this quickly. So what is the tangent of 45? Well, remember tangent is y over x. So if you look at this coordinate, y over x is clearly going to be the value 1. If you go over to tangent of 30, that's going to be a little bit more complicated. So this is the 30-degree coordinate. If we're doing the tangent of that, we have to do 1/2 over root 3 over 2. So from class, you know that you can simplify root 2's and get 1 over root 3 as your result. So luckily, we now know that these values are what they are, and they repeat down here. So we're going to get, again, these values on the right side. Now, I'm just going to get rid of this because we're going to need a little bit of space in order to make this happen. So if you see this setup that we have here, we're basically going to end up with the following. 1 minus 1 over root 3 and 1 plus 1 over root 3. So this is actually called a complex fraction. There are many ways to simplify a complex fraction, but the key is there's two things that are wrong with this. A, there's fractions within fractions. That's a no-go. You cannot leave an expression as a fraction within a fraction. So, for example, you're not going to go on an exam and you're not going to go, oh, the answer is 1 over 2/3. You don't leave it like that. You have to simplify it. The other problem is that there's a radical in the denominator somewhere. So these are the two things that we're going to have to sort of fix in order to come up with the final result. So how do you deal with complex fractions? There are a couple ways, but the easiest way to manage them is to multiply top and bottom by the least common denominator of every single fraction in the problem. Well, you can clearly see that the two 1's over on the left side have fractions of 1, so they're not going to come into play. So it looks like radical 3 is the least common denominator. So what we're going to do is we're going to multiply top and bottom by root 3. If we do that, we have to distribute, and we're going to get root 3 minus 1 over root 3 plus 1. Now, if you don't see that, take the time to do the math and peek to make sure all is good. Now, I'm going to rewrite this down here. So root 3 minus 1 over root 3 plus 1, because we're going to need some space, and just so that you're not confused, I'm going to eliminate it from over here. So now we're in a scenario where we don't have a fraction and a fraction anymore, which is fantastic, but we have this radical in the denominator. Now, I've done this before with you. I did a radical preview from algebra with you a while back where we talked about how when you rationalize an expression that just has one radical, a single expression in the denominator, it's very simple, but when you don't, you have to multiply by the conjugate of the denominator. So the conjugate is the same expression, but a different sign. Now, it just turns out that it's the same as what's on the top, but that is a coincidence in this problem, so don't think anything about it. I only care about the fact that, give me 1 second, I only care about the fact that this is the conjugate of this. That's it. The top being the same is a coincidence. So what do? We have to multiply this out. So these are scenarios where you have to FOIL. So I'm going to do the math over here. So what if I did root 3 minus 1 times root 3 minus 1? I would do root 3 times root 3, which is 3. My inside and outside terms are both root 3, and my last term is 1. If I add 3 and 1, I get 4. And if I combine the like radicals, I get minus 2 root 3. So the numerator of this is 4 minus 2 root 3. Let's take a peek at what root 3 plus 1 times root 3 minus 1 is equal to. Well, this is going to be the same 3. The outside is going to be minus root 3 again, but the inside is positive root 3. And the last is going to be minus 1. So this is by design that the radicals are actually going to cancel out. So if you do 3 minus 1, you're just going to get 2. So we get 2. Now, notice this worked. What was the purpose? It was to get rid of the radical in the denominator, and it definitely did that. So if we look at this really quick, we can actually simplify, because every element here, here, and here is divisible by 2, we can simplify and get 2 minus 3 as the answer to the problem. That is our exact value. So on exams, this is essentially what I would be looking for. I would be looking for you to take these values and find the exact ones using some variation of angles or values that you know. All right, so the same type of scenario can be applied to radian values as well. But that, of course, just like all changes from degrees to radians, can be a little complicated. So what does this problem ask? Number 3. It says, find the exact value of the cosine of 5 pi over 12. Okay, so 5 pi over 12 is clearly not a special angle that we know of. We only know of these types of special angles, pi over 6, pi over 4, pi over 3. So the idea of this type of problem is, can we find the cosine of 5 pi over 12 by turning it into the sum or difference of radian values that we know of? Well, they actually kind of give this to you. How do they do that? They tell you that the 5 pi over 12 is equal to the sum of pi over 4 and pi over 6. Well, just to prove that to you, if we do a common denominator here, we're going to get 3 pi over 12 for pi over 4, and 2 pi over 12 for 6, pi over 6. If we add them together, we get 5 pi over 12. So we should be able to then replace 5 pi over 12 with pi over 4 and pi over 6. Hopefully you see where this is going. Essentially, it's equivalent to what we did in degrees, but now it's in radians. So what do? Well, we follow again the formulas that we saw before. So we're looking for the cosine of a sum. So the cosine of a sum is equivalent to this guy right here. Cosine u, cosine v minus sine u minus sine v. So you would be looking at the formulas as you do this, obviously, but if you're going through the formula, you would be doing, again, cosine of our u, which is pi over 4, times the cosine of our v, which is pi over 6, minus, and how do we know it's minus? Because it's the cosine is always the opposite sign to what's here. And then the two sines with the same angles as what we saw before, pi over 4 and pi over 6. So we have these angles all set up. So if you know your trig, you know all these values pretty quickly. So any pi over 4 angle is root 2 over 2, root 2 over 2. If it's in the first quadrant for x or y, for sine or cosine. If you have the cosine of pi over 6, remember pi over 6 again is root 3 over 2, 1/2. So the cosine is going to be the x coordinate, and the sine is going to be the y coordinate. So we just have to plug in our minus sign here. If we do the math, we're going to get root 6 over 4 minus root 2 over 4 which is going to be equal to root 6 minus root 2 over 4. Now you're going to get, you'll notice that some of the answers that you get are going to be kind of similar. So like if you go back to number 1, we have a very similar type answer, not the same, but similar type answer. That does come up a lot based on how we function with these problems. So be aware of that. It's not the same thing, but then this would be the exact value of this specific problem. Okay, the formulas that we learned earlier here can not only go in the left to right direction, but of course they can go in the I meant left to right. Yeah. They can not only go in the left to right direction, but they can also go in the right to left direction. So what if you were given something on the right side? Could you change it into something on the left side? So we're kind of condensing. So if you look at this number 4, it's a sine of 73 cosine of 43 minus cosine of 73 sine of 43. So if the directions are to write each of the following trig functions of a single angle. So single angle. Notice we have multiple angles. So let's take a peek at the form of this. It's sine u cosine v minus cosine u sine v. So if you look carefully, that's the exact form. So we go, okay, where have we seen sine, cosine, cosine, sine with a minus between it? Okay, sine, cosine, cosine, sine with a minus between it. Looks like it's right here, which means we should be able to rewrite it as the sine of the difference of u and v. So let's do that. So this should be the same as the sine of the difference of u minus v, right? So let's now use our actual angles. So this should be the sine of 73 minus 43, which is equal to the sine, if you do the subtraction, of 30 degrees. So what's really neat about that is, of course, we can find the sine of 30 degrees because 30 is pi over 6, which is the coordinate root 3 over 2, 1/2. And we know that sine is the y coordinate, and in quadrant 1, that is, of course, just 1/2. Okay, we can do the same thing in terms of radians, right? So the same thing in terms of radians. We can look at this and say, well, what is our form of our equation? It looks like it's cosine u cosine v minus sine u sine v. All right, so where do we find that? Where do we find cosine, cosine, sine, sine with a minus between it? Well, we go up here. Cosine, cosine, sine, sine is strictly for cosine formulas. And when there's a minus between it, we're actually right here. So that would be the equivalent of the cosine of the sum of the two angles. So that's the equivalent of the cosine of the sum of the two angles, right? And remember the signs are different here with cosine, which is why this happened. So then we can rewrite this as the cosine of our u, which is pi over 10, plus our v, which is 3 pi over 20. Okay, a little bit different when it comes to radians because we need a common denominator for this. Note that pi over 10 needs to be changed to something pi over 20. Well, how do you do that? You multiply the top and the bottom by 2. So you're going to get 2 pi over 20. So this is going to be the cosine of 2 pi over 20 plus 3 pi over 20, which is 5 pi over 20. But if you're smart about this, you can see that this is simplifiable to get us to cosine of pi over 4. And look at that. That is, of course, in the first quadrant equal to the x-coordinate of pi over 4, root 2 over 2, root 2 over 2, which is, of course, root 2 over 2. Okay, so returning to concept you learned in section 5.1, in several of these sections, you will be asked to verify identities. Okay, you can also verify identities with pretty much any formula that you learn. So now we have new formulas, therefore new verifying identity problems. So If you look at number 6, you'll see that we have two sides of the equation as always, and our goal is to work from one side to the other to prove that they are the same. Left side, clearly more complicated. Therefore, we're going to look at this and say, let's start on the left-hand side, which is the sine of pi over 2 minus x. Okay, so again, what do you not want to do? Distribute the sign. So remember at the beginning of the lesson, it was proven that that does not work. The only way you can do a sign of a difference is to apply the sign of a difference formula. So again, if you look at the formulas that are all up here, we're looking for the sign of a difference formula, which is right here. So we need to apply this formula to what we need to work on with our proof. So what are we going to do? We're going to do just that. So what is this equivalent to? It's equivalent to sine, this is, by the way, this is u and this is v. So what are we going to do? Actually, let's make this a different color so you can see it all. So it's going to be the sine of u, which is pi over 2, times the cosine of v, which is x in this problem. Then the sine is always the same, S-I-G-N sign, is always the same for S-I-N-E sign of the difference problems. So then we're going to get cosine of pi over 2 and sine of x. Okay, what's unique about this problem? There's still variables involved, right? Whereas, on the other hand, we have these two quantities. Well, we can find these two quantities because these are quadrantal angles. So again, look at the unit circle. Pi over 2 is at the top, the upper part of the y-axis on the unit circle. And we know that the coordinate there is at 0, 1. So we should be able to find these very quickly. Why? Because the sine is the y-coordinate, which is 1. We can't do anything with cosine x. It has to stay. The cosine of pi over 2 is the x-coordinate up here, which is 0 times sine x. And if you do the math, this is just 0. And 1 times cosine is cosine. And look what we have. We have the right-hand side of the problem. So we essentially end up with a proof using the formula in terms of the sum or difference of a sine or cosine. So same thing can be done at the bottom here. So let's say we're looking at number 7. We have a tangent of a difference of x minus pi is equal to tangent x. Well, the tangent of the difference is another thing. You cannot, it's obviously the more complicated side, first of all. So we'll stick with that. Again, you cannot distribute the tangent. You must return to the tangent of a difference, which is right here, and apply this formula to what we have here. So what will that be? Well, let's do it. We have the tangent of our u, so tangent of u, which is our x, and then minus the tangent of our v, which is pi, over 1 minus, again, tangent x, and again, tangent pi, but multiplied. Okay, so if you look at this closely, again, let's look at our unit circle, right? We have pi is actually a half a rotation, so this is pi. So over here, we have the coordinate -1, 0, so we now can do our evaluation pretty easily. So we copy the tangent x, can't do anything there. The tangent of pi is going to be y over x, which is 0 over a -1, which is 0. We copy this, 1 minus tangent x again, but then we have a 0 being multiplied for tangent of pi. So if we simplify this, we're basically going to get 0 for this, which, so 1 minus 1 is, minus 0 is 1. And then on the top, tangent x minus 0 is tangent x. So the whole thing is equal to tangent x, which is equal to our right-hand side. So these proofs aren't so bad as long as you follow the rules in terms of the formulas They often do appear on exams, FYI, just because they are pretty quick to get through. Of course, you might also run into some more complicated looking problems. So just recall that even though we normally use x and theta for our angles, for our trig functions, any Greek letter is fine. So in this case, we're talking about alpha and beta here. So if you look at the two sides of this trig identity problem, verifying trig identity problem, you basically see that the left side is way more complicated. So we're going to start there. Want to save time, I'm not going to rewrite it. So if you look at this, the bottom, there's not really anything we can do right now. It's just sine times cosine with different angles. So there's nothing there. But if you look at the top is basically exactly what we've been doing. So if you look at the expression, it's the cosine of the difference of two angles. So you can go back to our ratios and go, oh, look at this. So we have the cosine of a difference, which is right here, which means we should be able to change the cosine of alpha minus beta into the equivalent expression if alpha was u and beta was v. So let's do that. So I'm going to get rid of this. So just remember. So let's just assume that this is u and v. So if we were to alter this, we would get cosine of alpha, cosine of beta, plus, remember the sign is different, sine of alpha, sine of beta. Okay, this is the equivalent to that upper expression. Then we rewrite sine alpha, cosine beta from the left side denominator. Okay, so if you look at these expressions, right now we have parts of the multiples in common, but not all of them. So what can't you do, which students will do? So first of all, you cannot cross out these sine alphas that are right here and here. Okay, you cannot do that. That is algebra illegalness. All right, and you can also not do the same thing with the cosine betas that are here and here. You cannot simplify that. So don't do so. So what is really the only thing we can do? Well, we have right now a scenario that looks like this. So let's say that you had 2 plus 3 over 7. Well, we know this is 5/7, of course, but what if we want to go in the opposite direction and we wanted to change this into two separate fractions? Why would we do that, first of all? Well, just look at the right side of this. If you look at the right side, you can see that there is a sum of two entities over here. So we want it to be the sum of two entities. If you look over here right now, we don't have that. This is not that, nor is this. So we want to break it into two pieces. How do we do that? Well, we want to break 2 plus 3 over 7 into two equivalent sum of fractions. So how do we do that? We keep the same denominator and we split up the numerators. Now, most of you, if you look at this side, you're going to go, oh yeah, that's the same as that. But it's not as always easy going the other way. It's just, it's not a typical thing your brain does. So just realize you can do that. And if you do that, you're going to end up with the following. Cosine alpha, cosine beta over the denominator, sine alpha, cosine beta, plus the other part of the sum in the top, sine alpha, sine beta, over the same denominator, sine alpha, cosine beta. Now, if you look at each one of these fractions separately, everything is multiplication and division. Therefore, you can now simplify. So if you're over here, you can clearly see that this and this simplify. If you're over on the right side, this guy on the right, then you can clearly see that sine alpha and sine alpha simplify. So therefore, you can rewrite your results and each one of these is a trig identity that you know of. For example, cosine over sine of the same angle is the cotangent of that angle. And sine over cosine of the same angle is the tangent of that angle. which is equal to our right-hand side. So just the general thought process on 7, 8, 9 with these identities. Eventually, the idea is that hopefully you get to the point where you start seeing things come together earlier in the problem. Not everybody gets there, but hopefully you do. That makes identities obviously much easier to accomplish. The last problem is a classic example found in sum and difference formula sections in many textbooks. It says, number 9, suppose that the sine of alpha equals 4/5 for a quadrant 2 angle alpha, and the sine of beta equals -1/2 for a quadrant 3 angle beta. Find the exact angle of each of the following. Okay, so these are two separate problems, essentially, A and B, but all the information goes with the one beginning part of this problem, which we want to start with. So there are two angles that they provide you, which is why you see two unit circles here, because each angle you want to try to draw out differently. So let's do that. This will be good review. You should be able to do this already, but review is always good, right? So we have a quadrant 2 angle, alpha, which is 4/5. So we're just going to draw a line. Doesn't matter where it is in quadrant 2. According to this, the sine of alpha opposite over hypotenuse is 4/5. Okay, so the only thing we need to do here is draw a reference triangle with a reference angle. This reference angle will basically be alpha for the sake of what we're doing here. So if we do opposite over opposite 4 over hypotenuse 5, then we're going to get this as the setup. So the question is what is the remaining side on the bottom? Well, we can do Pythagorean theorem and do 5 squared equals 4 squared plus x squared and go through the whole typical process. But I think most of you are going to remember that this is a 3, 4, 5 triangle, which means the side's got to be positive or -3. Clearly we're going to the left, so it's going to have to be -3. Okay, so that's alpha, our alpha triangle. What about beta? Well, beta is actually in quadrant 3 this time. Let's do a different color here. Quadrant 3. So we're going to draw a nice line in quadrant 3 and create a reference triangle. We're going to throw beta in here. So the sine of beta this time is 1/2. So that's going to be opposite, which is going to be here. So 1, but we know that's got to be negative because we're going down. And hypotenuse is going to be 2. Remember that the radius of the circle always must be positive. So this is not a special triangle. So why don't we go ahead and use the Pythagorean theorem for definitely in this scenario. Let's call it y squared, let's say. So we're going to get 4 is equal to 1 typo, righto, plus y squared. So we're going to get y squared is 3. Y is equal to plus or minus √3. So we look over this again and say, well, what is the top side of this have to be? It has to be -√3. Okay, so the beginning of the problem has nothing to do with what we need to find. It only has to do with setting up the figures so we can easily find any trig function value for them. As I've stated before, you need to become a master at doing this very quickly because it appears in many problems in the section. Make sure you can do it Pythagorean theorem quick. Make sure all the sides are where they need to go. Okay, so let's do the actual problem. So the sine of alpha plus beta, remember again, this is the sine of a sum. So we're returning to here, right there. So this is equal to sine, cosine, cosine, sine with a plus sign. So let's put that going on here. So we're going to do, this is equivalent to the sine of alpha, which is our u, times the cosine of beta, which is our v. And then we're going to put the same sign, because that's what happens with our sine sine function. Then cosine alpha, sine beta. Okay, so we actually know all these values now. All 4 trig functions we know because we have the triangles above. So for example, the sine of alpha was already given in the problem as 4/5. The cosine of beta was not provided in the problem. This was. So the cosine of beta, we need to go to our triangle here, and we have to say, well, cosine of beta is adjacent negative root 3 over hypotenuse 2 plus, now we're on the other side. The cosine of alpha was not provided, so we have to go over to our alpha over on the left over here, and we have to go, all right, well, we have to do cosine, which is adjacent negative 3 over hypotenuse 5. So notice a lot of negative signs are being used here. And the sine of beta was actually provided, which is going to be negative 1/2. Okay, so let's do the math here. So remember, if we do 4 times negative root 3, that's multiplication. We're just going to get negative 4 root 3, not root 12, negative root 12, or anything like that. We're going to get negative 4 root 3. And obviously 5 times 2 is 10. And then over here, a little easier math, we're going to get negative, these are both negative, so obviously the result's going to be positive. So 3 times 1 is 3, 5 times 2 is 10. We have common denominators, so we can say negative 4 root 3 plus 3, but let's just switch sides on that and get this as our exact answer. Now, just an FYI, when it comes to answers, normally you put the radical second. And the reason why that is, let me just go over here. So if you had like 2 plus root 3 versus root 3 plus 2, the problem is people can get a little bit crazy with their radical signs, and it might look like the root 3 and the 2 are underneath. So usually radicals actually go last, so this is the proper way to write it. So this would be our exact answer to the problem over here. 3 minus 4 root 3 over 10. Okay, finally, let's do the same thing over on the right side over here. The cosine of a sum. Okay, so if you go back here, the cosine of a sum is located right here. So it's cosine, cosine, sine, sine with a minus between them. So let's go ahead and do that. So this is going to be cosine alpha, cosine beta, minus sine alpha, sine beta. Okay, we know each of these values, not only in the triangles, but we actually found them all over here. So we can go right through this. Cosine of alpha is negative 3/5. Cosine of beta is negative root 3 over 2. Both of them we found over here. Right, here and here. Sine and alpha and sine of beta were both given as 4/5 and negative 1/2. So 4/5 and negative 1/2. Okay, doing the math, we're going to get negative 3 root 3. But oh, just to be clear, this is a negative right here. Oof. Gotta be careful. All right, so negative 3/5, negative 3 root 2 over 2 makes positive root 3 over 3 over 10. And we're over here, even though this is a positive and this is a negative, you have to pay attention to this over here, this negative, which makes the whole thing a positive. So you're going to get 4 over 10. And if you simplify, you're going to get 4 plus 3 root 3 over 10 as your result. So again, very similar looking answer, but that is the result of the problem.